Howdy folks, welcome back. Today we're going to be moving into a new type of analysis. So for the past several videos we've been talking about ANOVAs, which involve a nominal independent variable and a continuous dependent variable. But today we're going to be moving into something else. We're going to be talking about regressions. So if you'll remember from our bestiary table, we have regressions which have a continuous independent variable and a continuous dependent variable. So don't forget that our null hypothesis for a regression was that the slope of the line we're going to fit, or the regression, equals 0. Okay, so slope equals 0. And the slope is what we're most interested in with a regression. Basically that's how we're going to tell the direction of our test. So just a side note, when we perform a regression, we're always going to have our dependent continuous variable on our y-axis, and as I said in our bestiary video, this is continuous. It can be between any two numbers. This number could be 1,000. It could be whatever you want it to be. And we always say with a regression, we are regressing y on x, because x is causing an effect in y, but x is also a continuous variable. All right. Okay, so just to reiterate our null hypothesis, which is what we're testing, the null hypothesis would be no slope. All right, so I'm not going to cover all of the reasons we do a regression, but I'm going to cover 3 really important reasons to do a regression. So, reasons for regression. One of the first reasons is that we want to establish a functional relationship between our x and y variable. Okay, a functional relationship between our x and our y variable. So basically what we're doing is we're looking at y as a function of x. Okay, so y is a function of x. A second reason for doing a regression is that we assume a cause and effect relationship where variation in x causes variation in y. So changes in x cause changes in y. All right, and the third reason we do a regression, these are not independent of one another. We could have all these reasons for doing our regression. We don't have to pick or choose one. These are just 3 reasons we like regressions. The third is we have a plausible reason for thinking x causes variation in y. My eyes aren't being very clear. Variation in y. And I should say, since we're dealing with biological reasons, we have a plausible biological reason for thinking x causes variations in y. So what do I mean by a plausible biological mechanism? Well, we need to have some sort of hypothesis or reason, biological reason, we think that one of these variables is changing the other variable. So let's take, for example, body mass index and resting heart rate. And I'm just going to shorten them. So when we think of a biological mechanism for causing an effect, what do you think is more plausible? Do you think that body mass index, changes in body mass index leads to changes in resting heart rate? Or do you think that changes in resting heart rate lead to changes in body mass index? So think about that for a second. Think about the biological reasoning. Is it reasonable to think that just because our resting heart rate is higher, it's going to cause us to have a higher body mass index? Well, probably not, right? That's not really sound, but we do think that if you have a higher body mass index, that you're going to have a higher resting heart rate. So we have a biological mechanism for thinking that resting heart rate is changed as BMI changes. All right, so that's what we mean by biological mechanism. We mean that there needs to be some theory behind what you're regressing. So in this case, we're regressing our Y on X, or our resting heart rate on body mass index. All right. So let me just draw this to keep it in the back of our minds. Regressing Y on X, and we'd have a smattering of points to which we fit a line. Let me draw some more up here since I drew that line a little too high. So the basic formula for a linear regression is simply y equals a plus bx. And this is something I'm sure all of you are used to seeing. So what did these mean? Well, y is our dependent variable. A is our intercept. X is our independent variable. And importantly, B is our slope. And remember, slope is what we're interested in. And just to reiterate, the null hypothesis for a regression is that slope equals 0. So, does the slope we get from our regression have to be 0? Can it be positive? Can it be negative? Well, it can be positive, negative, or 0. So here's an example where we have no slope, which is our null hypothesis. An example where we have a positive slope, which would be our alternative hypothesis, right? Because we're hypothesizing that X does cause a change in Y. So that's a positive slope, and here would be our negative slope. So what this is telling us, and that would also be an alternative hypothesis. So this is telling us that as X increases, Y also increases. So positive changes in X are causing positive changes in Y. And this is telling us that positive changes in X, so as X increases in value, we're actually seeing a decrease in Y. We can have a negative, a positive, or a 0 value for our slope. So when we run our tests in SAS-JUMP, we're going to get a test statistic, just like we did with ANOVA. Our test statistic in ANOVA was F. For a regression, it's going to be R squared, and this is called the coefficient of determination. Now, in our next set of videos on a test called a correlation, we're going to get something very similar. We're going to get an R value. That is not the same thing as R squared, okay? So we're going to have to be really careful to keep those separated out because they're oftentimes confused. One is definitely for a correlation, one is definitely for a regression. For some reason it's not letting me erase that, so I'll just black it out. So R squared can be any value between 0 and 1. And 1 means that our regression, our line, perfectly fits the data. Okay, so an r-squared value of 1 means that our regression line perfectly fits our data. However, it's often very easy to do something we call overfit our data. So if we have a y here and we have an x here, we'll say, for example, I only have 2 data points. Okay, well, obviously my regression line is going to go right through those data points, and I'm going to have a perfect fit. I would have an r-squared of 1, but this is really not a great thing because that means we have overfit our data because there's no other option. It has to go between those 2 points. So if we want to avoid overfitting our regressions, it's important to have quite a few data points. That's why I've been drawing these regressions with many points, because we want to have enough points to get an accurate regression line and an accurate r-squared value. Okay, so what is r-squared? Give me just 1 second. There we go. All right, so r-squared is an estimate of the proportion, and notice I said proportion, of variation in y that is explained by variation in x. Okay, so r-squared is an estimate of the proportion of variation that we see in our dependent variable that's explained by the variation in our independent variable. So as our independent variable changes, how much of that variation in our dependent variable is being caused by that change. And I say proportion because it's genuinely a proportion. That's why r-squared is between 0 and 1. It's a proportion. All right, so typically what we see is the higher the r-squared value, the more variation in our dependent variable that is being explained by our independent variable. All right, so higher the r-squared value means the more variation in our y that is being explained by our x, or our independent variable. Our null hypothesis is that our slope equals 0. So when we actually run these tests in SAS-Jump, I'll point out to you on the data output where to find the significance of our tests. So in order for us to even say that some of the variation in y is explained by variation in x, we still have to have a p-value of less than 0.05. If we have a p-value greater than 0.05, or maybe more appropriately 0.1, because we consider anything below 0.1 a trend, then even if we have an r-squared value that does not equal 0, so something greater than 0, we still do not say that the variation in y is explained by x, because we don't have a truly significant difference, so the slope is not actually different than 0. So the first thing we want to look at when we do our regression is the p-value. And then after we establish that we have a difference, that slope does not equal 0, then we can go to our r-square and see how much of the variation or the proportion of variation in y explained by variation in x. So first thing we want to do is look at the p-value to see if slope is even different than 0, and then we want to look at the r-squared if we have a significant test. Just as a precursor, because we're going to talk about this a little bit later, but in our papers and in our presentations, when we report the regression that we did, we report the equation, including the slope, so y equals a plus bx, and we also report the r-square value. So the next video is going to be about how to run in regression in SAS Jump, and then we'll go through how to graph it in Excel. So I'll see you soon.